What I want you to do is write code to take the derivative of a polynomial.
Okay. So I remember that. I don't remember if a polynomial allows terms to have negative exponents or not.
Great question. Let's assume that they are all positive.
Okay.
Let you assume that.
Non-negative.
Non-negative,
Right.
yes.
Okay,
Thanks.
great. So how is the polynomial presented to us?
Excellent question. I will let you assume that it's taken in whatever format you'd like.
Okay, sure.
So
All right.
you probably don't want to make it a string unless you want to do a lot of string parsing.
Right. I'm thinking maybe in I was thinking an array initially. I still think an array would work, where the value at index I is the coefficient on the term with exponent I.
Okay.
So this array would be 2 at index 0, 5 at index 1, and 3 at index 2.
So this would be an array that basically looks like
2, 5, 3.
Or 3. Yeah. Sorry, you're doing the opposite way. Yeah.
Right.
2, 5, 3.
Right.
Okay.
All right.
So what might be a pros and cons of this versus or what other approaches can you think of, and why would you go with this one or a different one?
Well, I was thinking this because we know that for each exponent term, the only thing that identifies a polynomial uniquely is its coefficient. So it's very efficient in terms of size. So that's this provides all the information that we need about that polynomial compactly. And we're going to need to iterate through every value, through every coefficient regardless, so we don't really care about efficiency in looking up one coefficient or another. I mean, I suppose you could also have another hash map from exponent to coefficient. So this would be a map containing the key value pair 0, 2, 1, 5, 2, 3, and so on. One advantage to that may be that you may have a polynomial where you have many terms of large degree, but then you also have many 0 terms. So in the array,
like you have 3x to the 100th.
Exactly. Right. So for the array, you would need 100 entries. Many of them would be 0 and just taking up space. Whereas for the map, you just need a key value pair for each term that's present, each non-zero term.
So the key, okay, so one approach is you have an array. Another approach is you have a key value pair. What is the key, the exponent?
The key is the exponent.
Okay.
Yeah.
Any other approaches you could think of?
I mean, I suppose you could make a little struct or a little object called term that contains two numbers, the coefficient and the exponent. And then you could just have a set of terms. And maybe that would allow users to input polynomials that weren't simplified. So maybe at the end you have a plus x squared, which wouldn't suit. You'd have to simplify it yourself, or you wouldn't be able to send that into an array if you had an extra like term.
So that one allows. So we have sort of our three approaches.
Right.
One is an array, like 2, 5, 3.
Right.
And then the next one is a hash map, where we have like 0
to 2,
map to 2.
And then 1 to 5. And then
1 to 5.
2 to 3.
Then 2 to 3.
Right.
And the third one is an array of structs.
Yeah.
Okay. So what are sort of, so
or
this
a set
one,
of structs or whatever. Yeah.
Some sort of list.
Just some collection. Yeah.
Okay. So one pro here you mentioned is more flexibility. What might be some of the other pros of this approach? In terms of like time or space, or cons of time and space.
Right, so you have the same advantage as you did with the hash map, where you won't need an entry for 0 terms. And then one disadvantage is that you don't know if your structs are going to be in sorted order by exponent, which you see with the polynomial and you'd have with the array. So that makes it a little more, you'd have to sort it yourself to then compute the derivative efficiently. So that would be a major drawback.
I think one additional advantage here is just the clarity of using a struct. And it's just someone else is reading your code, and it's a little bit clear what's going on.
When you know that a term is precisely what the numbers
So how about we write the code, and let's go with this third approach here.
Okay, sure.
The array of structs, and we can erase this stuff.
Okay.
We might need to go onto the other board, but let's try to work with just one.
Okay. So can I assume that no two structs in the array will have the same exponent?
No.
I can't assume that. Okay, sure.
But you can handle that however you wish.
Sure.
It may not actually impact your code at all.
Right. That's true. Okay. Now, do I have to return the result in the most simplified form? Do I have to combine like terms?
Let's say no.
Okay.
Let's say, I'll make it a little bit easier on you.
Great.
That's a much harder